Okay, we got the recording started. Again, I'm at aeswave.com, and this is a source where you could get this low amps probe that we're going to show in the diagnostic case studies tonight. Is it something you absolutely have to have? No, you don't. Like, I've done a lot of testing without it, but it does make certain things kind of easy. But there's things I don't like about it either. And we'll talk more about that. I'm going to switch my screen share though to the PowerPoint, and this PowerPoint is on your is in your class under the modules tab, probably week 6 or 7, and we'll punch this thing up and get it going. All right, so we're going to start with a pretty simple circuit. For an example, the horn circuit. And what you have here is the horn circuit. This happens to be for, I want to say, a 2004 Cavalier or something. So pretty basic car, basic circuit here. What do we have as far as components? Well, if I kind of resize this thing. It's similar to what you're working on?
Yeah, I'm at work right now, working, listening.
Okay. All right.
I'll show you the horn.
You'll show me the horn here in a second. Hey, Victor, it's good to see you. See, you have a beard now too. You know, years ago you didn't have a big beard like that.
Yeah. Well, I don't know how. Hold on, let me flip the video. I don't know how to flip it.
Are you on a cell phone or a computer?
Cell phone.
Oh yeah, it should flip it. Although I don't know if it does it on Zoom.
No, I can't do it because you got that thing open, the confirm the problem.
Oh, well, no. Oh, no, you should be able to change your video. Even I'll stop my screen share real quick. Hang on. Did that do anything for you?
Basically like this one.
Uh-huh.
And then the horn relay is down here.
Uh-huh.
And then the basic horn.
That looks like that's a post office van right there, right?
Yeah, this is where I work.
Yeah. Hey, I heard they're gonna start getting in like little Mercedes vans or something in there. Is that true?
Yeah, it's usually over there in the back somewhere.
Oh, okay.
Got the 2 tons over there. But
all right, so turn around. I got to look at this post office truck. What is this thing? Is it it's a GM, right?
Yes, GM Iron Duke, the 2.5.
Oh yeah, the old Iron Duke. Yeah.
Yeah, and then there's a 2.2 over there.
That's super interesting. So the point here though is that this horn circuit, if I can find it, there it is, should be darn near identical to what would be on your post office trucks.
Yeah.
Very, very similar circuit. It's got a little relay in there. It's got your horn button. You can see in this diagram, we do have some
it doesn't have that
body control stuff, but the body control there is only monitoring what's going on for the most part. In that, you know, it can tell when you're pressing on the horn, or if you had a vehicle, let's say you had a factory alarm system, or even just a clicker on your keys, and if you click your keys, if it does the horn as you click your keys, or if you can do a panic button, this body control module hooked up here in parallel to your horn circuit here, right? This allows it to function the horn under those circumstances, right? So, you know, pretty simple circuit. There is some computer controls, and that perhaps with a bidirectional scan tool, I could hook up my scan tool and I could say, hey, turn the horn on, and I could see if it turned the horn on. In fact, if I did that, let me just draw my, I don't know, I'll draw a black box. Here's my scan tool here. And of course, if my scan tool then, he has a data cable hooking up to the diagnostic link. If I said, okay, I want to turn the horn on, and I had bidirectional controls with my scan tool, and I turned it on, and of course this horn started making noise when I did that, well, that would tell me that the horn itself is good and the relay works and the horn fuse works. In fact, if the customer's complaint was, hey, the horn doesn't work, if that's the problem, right? No functionality from the horn. I hit the button, it doesn't work. And I could walk up to this car and I could hook up my scan tool and function the horn from my scan tool. What would that tell me? What do you guys think? Not everybody at once now.
I think everybody's not understanding.
Okay, so if I could, if the customer brought me the car and they said, hey, I hit the horn button and the horn doesn't honk, but then I hooked up my scan tool and I hit a button on my scan tool and I said, hey man, turn the horn on, and I hit the button on my scan tool and the horn turns on and it starts making noise when I command it on with my scan tool. What have I just diagnosed then?
The horn relay is not working?
No. Okay,
wouldn't it
so
be the switch?
yeah, exactly. What we're saying then is that my switch in the steering wheel, right, is not working because everything else from here to here, all this stuff's working. So the rest of the circuit's good. It's got to be the horn switch. Now, wait a minute. Let me back up. Let's say I don't have a fancy scan tool with bidirectional controls that can turn the horn on. It has that capability, right? Maybe I don't have that. Maybe all I have is some like OBD2 generics cheapo scan tool, and the customer says, hey, the horn doesn't work. That's my problem. No horn function when I hit the button. Is there some other way I could test the horn really quickly?
Yeah, check the relay.
I could check the relay. I'm thinking even easier. If I had a key clicker that had a panic button on the key clicker, and I could hit the panic button on my keys, right? That would send a radio signal to, again, this body control module, and it should make the horn honk, right? So if I hit the key clicker and the panic button and it starts honking, then again, that does the same thing I did with my scan tool, and it tested the complete circuit, right? The relay, the fuse, all that stuff. I'm only bypassing the button in my steering wheel at that point and the little bit of wiring there going up to the relay. I bypass a lot of circuit by doing that. So what I first want to point you out is that even though this is a meter class, if there's ways that I can test the circuit without having to break out my meter, I want to do that because quite frankly, it'll be a lot faster for me, right? And, time is money and we want to make accurate decisions, but we want to make those decisions as quickly as possible. So sometimes it pays you big dividends to, before you pull out your meter or, you confirm the problem, hey, the horn doesn't work, get the diagram. Look at it and figure out how the circuit works. If you saw something like we had right here, that would be your clue is, oh, maybe I could function this horn with the key fob or maybe with my scan tool or something like that. And that might give me some really good information. Okay, so let's say the horn doesn't work. So no horn operation, and I can't get it to work by functioning the keys or anything like that. Okay, and this is my circuit. All right, well, moving right along then, I'm gonna show you that current probe that I was showing you on AES Wave's website. I could hook that up to that circuit. Now, wait a minute. What if I don't have one of those probes because that stupid thing cost me $100, right? If I kind of know how much current a horn should take, it would send me in a, you know, I can make an educated guess, and I could do that off of this fuse right here. Like this fuse shows that it's a 15 amp fuse, right? Now that fuse might run other stuff besides the horn. Usually horns will run at less than 10 amps, okay? So knowing that, I could decide, I could say, okay, you know what? I'm going to unplug the horn fuse. I'm going to take one lead here from this meter and hook it up there. And I'm going to take my other lead, set him to amps, put the meter on a 10 amp scale. So I'll move it like that. And I could have the current flowing directly through the meter. The downside of doing this is that my meter is vulnerable to getting the fuse blown out of it, and I could possibly damage the meter if there was a big short or something in the circuit, right? However, if there was a big short in the circuit, the fuse hopefully would blow. So, you know, there is a little risk there, but you could certainly do that and put your meter in series, take the fuse out, put your meter in series with the circuit, just like I've drawn, okay? And then try to turn on the horn and see what happens, right? So the only reason that in this, this example, instead of hooking the meter up in series, I have us attaching a current probe is it's a little safer, right? You're not going to risk damaging your meter or blowing the fuse out in it if you use a low current probe. But anyways, you could test this directly by measuring the amperage through the circuit, because remember, what does the work? It's the amperage. So you got to make some decisions based on what you measure there. So I'm going to try to hit the button to my next. All right, so we zeroed the current probe. We pressed on the horn button, and we're going to record the flow. And I got some different reading here, different possibilities, okay? Now, what would these different things mean? Well, in theory, if I'm flowing 6 amps or more, I really should have the horns working, because that's about 6, 7, maybe 8 amps. That's what a normal automotive horn will pull. If I was down here, well, that would tell me part of the circuit's working, but it's definitely not flowing enough current to activate a horn. So something's wrong. I must have some resistance in there. What do you think about this little tiny bit of current flow? Let's say I'm only moving like 0.5 amps, right? I mean, that's still some current flow, but it's not very much, right? It's less than 1 amp. What do you think is going to take about 0.5 amps? Well, a relay would take maybe about a half an amp if I was just running the relay. So if I was at this scale, I would think, oh, well, you know, maybe the relay's clicking, but maybe the actual contacts of the relay aren't closing, or something else is going wrong. And of course, if I have no amps flowing, I probably have just a big open somewhere in the circuit, okay?
Does that apply to trucks too? Semi-trucks?
A semi-truck, well, yes, it does, but a semi-truck horn's probably going to pull more amps. They usually have multiple horns in there in parallel, so you're more likely to be pulling 10 to 12 amps for a semi-truck horn. So again, on a semi-truck horn, I would definitely want to use that low current probe so that I didn't damage my meter, okay? But if it was like a Miata or something small and it's got one little dinky horn, this lines up perfectly with that, okay?
Gotcha.
All right, so the idea is that if I can measure the current flow, I can make some quick determinations as to what do I want to check next and where, type of thing. All right, so let me clear out these scribbles that I have on my screen, and we'll go to the next slide. So we are going to, oops. do our first scenario. So we hit the horn button, boom, and our meter basically says all zeros. Okay, we got no current flow at all, right? So we have no current flowing. I'm gonna draw my Ohm's law pie chart up here with volts, amps, and ohms. If I have no current flowing, basically there's no amps, and if I have 12 volts at my battery, like the battery's good, what does that tell you? The ohms has to be big, or essentially I have an open circuit, right? This is supposed to say open. It's really hard to draw with my mouse there, but if I got zeros here, hey man, I got an open circuit in this thing. So again, I'm probably gonna still go to the same spot for a lot of my tests. Now, in this case, you can see like the way we kind of did this graphic, we drew the low amps probe right here. That low amps probe, it'll actually fit around most battery cables. So I could clamp it around the battery cable. I could even clamp it around the negative battery cable if I wanted to, but I could clamp it around a battery cable, zero it out. So if there was any like dome lights on, anything like that, that were pulling a few amps, I could zero it out and cancel those out, and then see what it changed to when I hit the button for the horn. In this case, what we're saying is we saw no change in the amount of current flowing through these wires when I hit the horn. So I could have a blown fuse, I could have a dead relay. In fact, those are my most likely things, or the wiring here could be open, but here's some stuff I know it's not, okay? Let's say, for instance, the horn was disconnected. Like maybe I just walked over, my coworker at work was messing with me and he just unplugged the horn when I was on my lunch break or something, right? Well, guess what? If the horn was unplugged, but the relay was still hooked up, if I hit the button, I should still see maybe 0.3, 0.5 amps, because that's how much current would have to flow through this circuit to activate this little coil inside the relay and make the relay go click and turn on, right? So because I see no current flow, that tells me that it basically has to, my problem would have to be, let me clear this out here. My problem would have to be on this side forward, basically, right? It would have to be an open somewhere. It could be an open relay. It could be open at the fuse, so either one of these things, I'm going to go to what's easiest. Now this is lower left side of dash, left end of dash. I'm going to go to whatever is easiest and start my testing there, probably straight to the relay and see what's going on. And maybe I'll just do a relay swap. I'll just swap it and see what happens real quick, right? But do you see how seeing the current flow kind of lets you know what side of the circuit the issue is on, right? So if I have nothing there, I think, okay, I must have an open circuit somewhere, and it's got to be on the relay side forward, right? So then I could get my regular DVOM out. In fact, I'm going to clear out these drawings, and I'm going to go back a couple pictures where it just shows the meter with it. And I could set this meter up to volts like it is, and start hooking up my my leads and testing voltage drop at various spots. So I could hook this over to ground, and I could take my positive probe and just start seeing where I'm at. Do I have 12 volts here? Okay. Do I have 12 volts going to the relay there? Okay. and just start kind of going through the food chain here to see where my problem is. I could have a situation where maybe the horn switch isn't providing ground to the relay, but remember, I would also have at this point saw if I could function the horn a different way as well. So anyways, having the current flow there kind of helps you divide stuff out. And what we're trying to do is figure out what's wrong with a minimal amount of digging around in the wiring of the car, right? Always remember there's like 5 miles of wire in the average late model car. We want to do the least amount of digging possible. So now we're moving right along, and our scenario 2 is, oh, I'm flowing 0.015 amps. I'm flowing basically 15 milliamps. Just a little bit of current is flowing now.
So what if you have corrosion on the fuse? That gives more resistance, right?
That would give more resistance. In fact, that might give it enough resistance where it doesn't work. And again, if you're flowing less current flow than you expect to flow, you know you have a resistance problem. And what's your next step? Once you verify this, once you see this, you're going to be like, okay, I'm jumping into voltage drop tests.
Okay.
So if I had this issue right here, what I would think is that, oh, my horn relay is trying to work because I am getting some current flowing through the circuit, right? So what did that tell me? Well, the fuse the fuse can't be blown. It's got to have some functionality there, and my switch here probably is working because I'm functioning the relay, and the control side of the relay is working, but maybe these actual switch contacts over here are not working, and that's why the horn actually doesn't make sound, right? So simple bad relay. Again, you'd probably just swap relays with something else and see what worked. But you can see now that I have a little bit more current, the situation's definitely changed, right? So let's clear that out of there. And we're gonna go up a little bit more. So now we're definitely getting full functionality out of the relay, because now we're flowing 150 milliamps. But the horn's not turning on, right? So again, I would be swapping relays. I definitely feel like all this stuff is good, and I'm not going to jump into the same voltage drop test I did before. In fact, I'm going to swap relays. If that doesn't work, I'm probably going to go straight, to testing the relay in this circuitry over here. Okay. So now we go to this one. Now, this is kind of weird how this displays it. It says 0.783 amps, but or 0.783 volts. But really, what this is saying is it's flowing 7.8 amps. That's what's kind of weird about these low current probes, is you got to think, okay, what scale am I on? And did the thing auto range on me? But basically, this is indicating, hey, the horns aren't making sound, but I'm flowing almost 8 amps. So now this is a different scenario. This basically tells you that this circuit's good and the relay's clicking and it's trying to flow current through the horn. So, and in fact, it is flowing current through the horn. It's flowing almost 8 amps, but if the horn's not making sound, there's probably actually a mechanical problem right in the horn, right? So, why would this current probe make sense? Well, it could potentially save you a lot of time, because if I had this number, then I'm not even going to worry about going through and testing a relay. I'm going to go straight at the horn. Whereas if I had, let me back this up, a different reading, like I have right here, then I would be like, okay, well, I think the control circuit's working, but the actual relay's probably not working correctly. Its contacts aren't closing. Versus this, I think, okay, I definitely have an open in the circuit that's either related to the grounding of the relay, or it's before the relay itself. So it basically, it's a pretty fast and easy way to kind of help narrow you into the right direction. Okay. And it's a good way for me to, you know, kind of stress that. Remember, it's the current that does the work in the circuit. Oftentimes we don't think about how many amps things flow, but if you know that type of stuff, it does kind of help you in your diagnostics. So one of the things I did when I first got my low amps probe is I would just start testing stuff that worked, you know, that there's no problem with it. I would just test it and see, well, how many amps does a horn flow? Oh, okay, this one works. It sounds good. It flows this many amps. How many amps does this cooling fan pull? How many amps does this fuel pump pull? So, and I'd start writing that down in my little notebook. So I kind of had an idea of what I should expect from different types of automotive components. And then that helped me identify when I had something wrong. Now, if you work at a dealership or a fleet like Victor, right, you know, he can probably grab a different vehicle that is working and compare one to the other, right, and figure that stuff out. When you're working at an independent shop where maybe you have a lot of cars that are different, you don't get to do that as much. What's that?
That's not usually you have a lot of spare parts in your toolbox.
Oh yeah, yeah. Like any good dealer or fleet tech, lots of good known parts, right?
Yeah. So if you have a relay, you can switch it out very quick, and then test it.
Exactly. Okay, so let me keep blowing this thing forward. So we kind of get the different scenarios and how you can look at the current flow and kind of help use that to help you narrow things down. Now, here is the complaint here. This is kind of a interesting one. Passenger side window was put down, but it won't go back up. Where do you start? And this is a pain in the butt, right? Because it's always, oh, the window went down, now it won't go up, and it's going to rain or something, right? So we're let me ask you guys, like, where would you start with this type of situation where the passenger window goes down? However,
so at the green wire right there at the switch, and the blue one.
Well, before that, right, I would try to see like what is everything that I can do to test this thing out, and what things are linked that I can eliminate by functioning stuff. Like you can see, I have
the modules working on the switch on top.
Well, because if the complaint doesn't say that there's anything wrong with the driver side window, right? And so here we can see two different window motors. And I need to do something here real quick. Oops. I'll get the screen share going again. Just hang on a second, guys. There it is. All right. Okay, now wait a minute. All right, are you guys seeing my, yeah, you should be seeing my display. I wanted to just make sure that we had the lay of the land here, so to speak, in that here's the passenger motor over here, right? And then here's the driver's side motor there. And you can see that your driver's side switch, right? The driver's switch is always like your master on a Windows circuit, right? In fact, oftentimes these days, a driver's window switch is a computer that's on the network that's talking to the other computers. And maybe that guy doesn't have power flow through it directly. He's just sending signals to the body control module, okay? This vehicle example is not that new. So it actually has current flowing through the window switch. And what that means is that the current would have to flow through first it would have to flow through first the driver's side switch. If I can change my marker, it's got to flow through the driver's side switch and then come through here through the passenger side. Like these guys are both the passenger side switch, if you will, is in series with the driver's side. So where would I start? I would typically start on the driver's side switch. If I couldn't control the passenger window from either switch, it makes sense to start over on this side, right?
Actually, they started on the scan tool remotely.
I could. What I don't see on this circuit is I don't see any computer controls, right? Like if this thing had a, let me change colors. I'll do a different drawing here. Let's say it had a wire that went from that and it said to a box and it said to BCM, right? Well, then that would lead me to believe body control module. That would lead me to believe that, hey, I could use my scan tool and maybe try to function these windows with the scan tool. But I don't see anything like that on this particular picture. So that tells me where do you?
Since it doesn't have a module, it'd be like pre-96, very old.
Oh yeah, pre-96. I thought you said look for pin 96. I'm like, there's no pin 96 in here. Yeah. Basically, we're looking at an older car, or maybe a car that could even be later 90s, but it would be like a base model, something like that. Okay, so no computer controlled windows on this thing, right? It's basic car. You know, it's not so basic that you have a manual window, but it's still pretty basic in that the computer's not tying in the windows. So now what we're going to do is I'm going to clear those drawings. I'm going to make the screen I'm going to make the screen larger on my end, and I'm going to fast forward this thing, and I'm going to remove just the wiring to the driver's side window, since that works, just to make this easier for us to kind of visualize. So this is our focus here. So if I can get this going now. Okay, so we're going to do the same activity where we use the low amps probe. Now this would be a circuit where I could not wire my meter in series with the circuit, because a power window motor is going to pull way more than 10 amps of current. Okay, I would expect it to pull anywhere from maybe 13 on the low side, 12 or 13 on the low side, to maybe up to 25, depending upon how big the window was that it's moving. So it's going to be more of an amp hungry circuit. So they hook up the low amps probe here. And again, that low amps probe could just be around the positive battery cable. And I just hook it up there. If I have to have the ignition key on, I can turn that on. I can hit this blue button on my low amps probe. I could push that button and then that would zero it out. So if it took, I don't know, 10 amps just to have the key on engine off, I could make that read 0 by pushing the blue button. Okay. And now I hit my driver's side window trying to turn on the passenger window. So I turn on these controls right here and I see, well, what the heck happens? So we're going to hit that guy and we're going to go down. And what I'm going to do with you guys is I'm going to try to trace that circuit. So we want the driver's side switch in the down position, right? So let's start drawing some of that stuff in here. Okay, so you can see if I just think, well, how does current flow through this thing? A couple notes is that power windows, they take more power, they take more current flow, and they will commonly be ran off of not just a regular fuse, but a circuit breaker. Okay. Why is that? Well, if something physically gets in the way of the window as it's moving, like bogs it down, we want the circuit breaker to pop to protect the wiring, but we don't want to blow a fuse and now the window won't work again. So like a circuit breaker in your house, this one could be reset. A lot of these, as they cool off, will reset automatically. So it has a circuit breaker here instead of a fuse. So how does this thing, how's this sucker work? Well, if I'm using the driver's side, what would happen is current would flow through there. I'm saying I want the right side to be down. So I have the switch contact in the down position. It's then going to flow through the passenger switch. Then it goes through the motor. Voltage drops through the motor, but the current keeps flowing. And it goes down to there. And then that goes back through the switch, and that's how it gets to ground, right? So that's how current flows. In fact, I tried to do this when I labeled the wires. Anything that I labeled blue, if I were to put my voltmeter on it, it would say 0 volts. Oops, I guess I should make that a 0 volts. And anything here that I labeled red, if I put my voltmeter on it, should say, oops, should say 12 volts. Get that going. Okay, so what do I mean by that? Well, if I took this meter and I set them to measure volts, and I took the negative probe and I went to ground, and I took the positive probe and I went right here at the switch, I should measure 12 volts right there. In fact, if I went to this pin while I'm pressing the down button, I should measure 12 volts right there. If I unplug the passenger window switch and hit the button, where not that the window switch is the wiring's unplugged, but I pulled it out so I could access it and back probe it, I would measure 12 volts right there. Anything on the downside, anything that I done here blue should measure 0 volts, because where do I drop my voltage? I drop it across the motor of the power window switch there. Or I'm sorry, the power window motor. Anyways, all right. So we will erase some of these scribbles. All right. So we've traced the circuit and kind of figured out, okay, how it works. Moving forward then, let's say our test result was 0.00 amps. Basically, this meter said nothing. It says 0. Well, what would that tell us? Oops. Well, if it said 0, I'm not flowing any current at all. So do I have an open or do I have a short? What do you guys think?
Wouldn't that be an open?
Yes, exactly. That tells me I have no current flow. I have to have an open somewhere, right? And so if I have an open, then I'm going to jump into voltage drop testing, and I'm going to start breaking down the circuit where it's easiest to get to. So maybe I go after the circuit breaker. Usually it's pretty easy to remove, like the driver's power window switch, remove that guy and start doing some back probing. But I'm jumped into voltage drop checks and finding where I have voltage or where I don't have voltage and I should, or where I have voltage when I shouldn't. For instance, now I have them labeled black, which should be 0 volts here, and red should measure 12 volts, right? So if I pulled out the window switch and I back probed it and I'm hitting the down button with my finger, again, I can get this set up right. I got one lead here, my negative lead's going to ground, and my positive lead, if I went right there, I would expect the meter to read what? What color is it? We've labeled it red, right? So I would expect the meter to read 12 volts. Now, if I said, okay, I'm not doing that, I'm going to move this lead, and now I'm going to move him down. I'm going to move him over here from, this was, I probed it at connection point G here. I'm going to go over here to F. On F, I should measure 0 volts, right? Or something very close to 0 volts. There might be just a little bit of resistance in some of these connections. So maybe I would measure like 0.01 volts or something, but something very close to 0. But let's say here, I'm not measuring 0 volts. Let's say I'm still measuring 12 volts. I'm trying to write 12 in there. Oh, I know what I can do. Hang on. We can go like this, and I will put this right there. So it's saying 12 volts. Well, that actually did not work how I wanted it to, but you get the idea. It says 12 volts on my meter screen. I'll put them over here so we can actually read it. So this would tell me something different, right? I know I have an open, I know no current is flowing. If I see 12 volts over here, you know what that tells me? That tells me that I must have an open here, and it's got to be after point F. So it could be an open on in the driver's door switch. It could be a bad ground right here. Let me draw out what would go down here. Let's say this ground splice pack thing is broken, or somebody was working on it and they were below left side of driver's seat. Maybe somebody took the driver's seat out and they didn't put that wire back on, right? Now it has no connection to ground, so current can't flow. And so even though there's resistance at the motor right here, because no current's able to flow, because that point being disconnected right there, this would just be reading 12 volts all the way to right here, okay? And it would tell me, oh, I must have an open on my ground circuit, right? And I could start testing it at different spots. I could start, I can move my meter lead. Now I'm gonna move it over to terminal B. If I don't see anything there at terminal B, then I'm gonna go straight here and see what's going on there. So if you're not measuring any current flow at all, you know, hey, I have an open circuit. That screams, I got an open. I'm jumping into voltage drop checks, and I see where either I should have voltage and there's nothing there that told me, okay, I found that open, or maybe I have voltage on the ground side where I shouldn't, right? So again, voltage drop or measuring voltage with your meter is the most common measurement you're going to do. And that's a good example of how, yeah, we actually started off by measuring current in this activity, but then that, based on what that told us, is what indicated next that our next test we needed to do was voltage drop testing. So, all right, so different scenario. Scenario 2 now is that now you're reading 6 amps. Now remember, 6 amps, oops. 6 amps really isn't enough to make the power window work. So what that means is that I am flowing some current, a substantial amount of current. However, this is not enough to actually get the window to lift the motor, okay? So if I redraw, go ahead, say it again. I would expect a power window motor. Remember, I'm measuring amps here, and I'm measuring the amps. If I go back, I'm measuring it.
So yeah, you need 12 amps to roll it up.
Yeah, I need 12 amps. So now what we're saying is the meter is telling us, hey dude, you're measuring 6 amps. Okay, so I need 12, somewhere between 12 to 15 to get this thing to roll up. That's not enough, but it is flowing some current. So this is definitely a different scenario in that now
What if you got
I
a bad
must have
battery?
current. I got to have current flowing through there because I'm measuring it, right? That means that there's got to be a complete path through the switch, through the other switch, through the motor to ground. I have to have a complete path. But you know what I have? If the current flow, the amps are still too low, that means the resistance has to be too high. So I'm still in there doing voltage drop tests, but I'm not expecting to find an open circuit. I'm expecting to find high resistance somewhere. So it's a little bit of a different breakdown. I would be hooking up my meter. I'd switch it over to volts, and I do the same. I'd be measuring at the same spots. So if I take this sucker and I take one lead and I go, okay, that lead goes to ground, and I took that positive lead then, and I first went over here to G, I would expect to see 12 volts right there. If then I went over here to that, if I then went over here to C, I would still expect to see 12 volts. If I was hitting the button and I was probing here at C and I had 12 volts here, but over here I have, I don't know, maybe over here I have less, I have 8 volts or something. What that told me is that I dropped 4 volts across this switch right in this section here. I'll change that color. So I have high resistance in my window switch, right? So I just start going around here, and everywhere that's labeled red, oops, come on, eraser, gets everywhere that's labeled red on the way we've traced up the circuit, my meter should measure 12 volts or pretty darn close to 12 volts. Everywhere that's labeled black should measure 0 volts or pretty darn close to 0 volts, right? And what you would likely find is at one of these points, it's not going to read that. You're going to be dropping some voltage due to resistance somewhere. It could be resistance at a connection at a window switch, or at the motor itself, or in the switch itself, or at the ground. I could, what would happen is I wouldn't have even had 12 volts right here, right? So it would be something less. So remember, the advantage of getting the diagram out and tracing it with some colors is that it kind of tells you when you look at the diagram, okay, anything I traced with the red Sharpie pen or the red highlighter, pink highlighter, that wire should have close to 12 volts on it when I test it with my meter. And anything I highlighted, let's say with a dark or a black or blue highlighter, I should measure 0 volts there or pretty darn close to it. It's an easy way in your mind to walk up to the car and know what you should expect to measure at each point in the car. And then if what you measure doesn't match with what you expected to measure, you found your problem, or at least you've identified, hey, that's different than what I expected. Let me think about it again. Why is it different than what I expected? And if you thought about it, how it worked correctly, then that means you just found your problem. So if we do one last scenario, which was the window doesn't go up, but it's pulling 15 amps, right? So now if I go back to this picture, if this sucker now is pulling 15 amps, well, that's enough to make, it should make the window move. So if it's pulling that much power, I'm pretty much going to jump right into going straight here. I'm ripping off the door panel. I'm going straight after the motor. or maybe the regulator that helps the motor do its job. There's something mechanically wrong going on. That electrically, it's flowing the right amount of current. If the window's not moving, I must have some type of mechanical problem, so I can go right into working on the motor itself. Now, I use that word regulator for those of you who have never taken a door apart before. Well, one, you're lucky, because taking apart doors is kind of a pain and fighting those windows and stuff. But if you've ever looked at a garage door, right, in your garage door, there's usually going to be like some springs to help you lift the door open, whether it's a coiled spring that winds up like that, or it's just big springs on the side that help you lift the weight of the door. Your typical car is going to have some type of spring mechanism somehow that's going to help the window help the window motor lift up the window. And so we call that, in car speak, we call that the regulator. So, in this case, if I'm pulling the right amount of current, window's not moving, mechanical issue, maybe a window motor, maybe a regulator, maybe some of the hinges or something in there are messed up, something like that. Window track's broken, but it tells me I got a mechanical problem, not just an electrical problem. So that being able to measure current flow can save you some time if you know what current you should be flowing for different circuits, like if you know what to expect. Okay. And so that's kind of like my overall tech tip. If you know what to expect for current flow, it can really save you a lot of time there.
This is all on the quiz, huh?
No, this is not on the quiz. This is kind of over and beyond the quiz. But in the class, I really want to show you like other ways to use your meter. So let's exit out of this thing, so I can see we're running out of time. And what we're going to do is I'm going to change my screen share and go back to the internet. There we go. And with that, we'll go back to our Canvas class and see where we're at. If we go to modules, remember everything's under those modules. And we're going to scroll down here to week. We're really in week 7, but we're actually kind of running a little bit behind. So this presentation we just went through is this one from week 6. So even though technically this is week 7, we're running a little behind, and we're going through week 6 material. Now, when is stuff due? Stuff is always due further back than that. In fact, what I will do, because that takes a while to load, is I'm going to punch up our course calendar. And once the calendar loads, my kids must be watching something on Netflix or something, because my internet's being super slow. All right, so what do we have for this week? We have a little discussion, and there's a little quiz, and we'll look at those. Next week is some charging and starting system stuff. So the assignments are always kind of lagging behind a little bit to give you time to view stuff. I know it takes me sometimes a couple days to get our class session, get the recording posted on YouTube. And so my concern is if people aren't able to attend the class sessions, that this allows them enough time to do that. So we'll look at what's due this Saturday, okay? But it's a little bit further behind than what we just lectured on, which was kind of ways to flex your diagnostic muscles in different ways to use your meter to diagnose problems. What we'll do next week is I'll have another case study for you that we'll go over next week. That's all about a no-start diagnostic where you're using your meter and stuff again. We'll do a little bit of low amps probe testing with that as well. All right, so let's go back into our class and let's look at this stuff that is due this Saturday. So I could go to modules. Another way to do it, if your concern is like, hey, what's due when is just click the assignments tab, and I can kind of look on the dates. Now let's see, this Saturday is going to be what, October, what is it, 9th, 10th, something like that. So we have a discussion coming up, and where is it? Here it is. The future of the auto industry and you. Okay, so this is not something super technical. It's just to get you guys thinking about it. And I think we talked about this last week as well. Governor Newsom has basically signed kind of like a governor's executive order, if you will.
We're exempt. Post office is exempt.
Yeah, you guys are exempt at the post office. But anyways, he's done an executive order to ban, keeps wanting to play an ad, to ban the sale of gasoline-powered cars by 2035. The idea is that then trucks and stuff would follow that maybe another 10, 15 years later. But it's just to get you guys thinking about it. How can you be prepared in the industry to deal with this stuff? Now, of course, you know, this was signed by the governor. So if we change governors, right, as politics change, this could change, right? This could be pushed back. It could be modified where instead of banning all cars, maybe it's 80% of the cars have to be zero emission vehicle and 20% can still be powered by internal combustion engines or something, right? So I expect that this will probably change, but some portion of this will probably carry forward, and that will impact us all. So this discussion is just to get you guys thinking about it. How is it going to impact you? What skills do you think you would have to add to your resume? What knowledge should you have to be ready for this type of stuff? And then it's just kind of fun. Are you excited about this? Are you pessimistic, right? Are you anxious? You're like, oh, this is terrible, or, oh, this is awesome, or I'm ready for anything, you know. So that's very light assignment just to kind of get you thinking about stuff in the future.
More money for
What's
tools.
going down. And you know, you never know for the post office, Victor. You know, for a lot of things, an electric vehicle might make sense. Like for fleets
Well,
can really
we
leverage
have
this
hybrid
stuff.
already.
Yeah. Well, because if I'm a fleet and I know, okay, this vehicle, you know, vehicle number 100, it does a route every day, and that route is, I don't know, 42 miles of driving in these conditions, and at the end of the day, it returns back to the yard. Then if I have that all mapped out, that's where an electric vehicle can work really well, because I know what my driving patterns are, right? If we think about like regional transit back in the 90s, went to compressed natural gas for their buses. And it's kind of the same thing. They would have to fill them up at the bus yard every night, but they knew how far the bus would go each day. And they then knew, well, how much fuel it would consume, and they could plan stuff out accordingly. So long distance buses wouldn't be running compressed natural gas, but the ones that had to go shorter distances, those could run off that no problem. So for a lot of fleets, they can kind of get tax credits and additional benefits and lower their operating costs sometimes by switching to alternative fuel vehicles, because you're not planning for the unexpected, right? Consumers, like when I buy, let's say I'm going to buy a pickup truck, I'm like, well, I tow my big trailer every once in a while, so I better get a 3/4 ton, even though 90% of the time I'm just driving it down to Home Depot and a 1/2 ton would have done just fine, right? So when you're you know, purchasing cars for a fleet, it's a little bit different deal, and you can really zero in what your needs are. Anyways, that's this assignment. Okay, so for Saturday, what you want to do is respond to this little discussion. Okay, it also said there's a quiz coming up. If I go back to the assignment tab, I can find it.
It's on Saturday.
Saturday. What did I say? Sunday?
Yeah, I
I'm
don't
gonna
know.
go here. And you know what I'm gonna do? I'm gonna hit student view, because I forget sometimes that my screen will look a little different than yours, but assignments, and lab quiz sheet number 2, basic meter knowledge. Let's check that out. So this thing's pretty simple. It's not like crazy stuff. It's how do you basically use a meter. Now I've used the Snap-on meter for an example, but all the questions I selected would apply to anything, whether you're using a Snap-on meter or a $10 Harbor Freight meter, okay? So what does it mean when you have high impedance? You know, looking at that, what jacks are you going to use for what? Measuring stuff in ohms, category ratings of the meter. So pretty basic, straightforward thing, okay? So that's what you got coming up. Now, I always like to end on a tech tip. And I kind of feel like in some ways, our entire class today was a tech tip about like using low amps probes and how you can leverage that stuff. But I always like to end on just a tech tip that you can use with your meter. So what I'm going to do is I'm going to change my screen share one more time. I'm going to go to this, I think. Let's see. Yeah, I'm sharing my screen. And I'm going to close a couple of things out here. Yeah. And so what I had to do this week is I had to take, this is my school computer. Actually, it was the computer that would run our dyno. And my like work laptop crapped out. And so I took it from, you know, I took it off the dyno and I brought it home basically. And then I forgot the cords for it. And then I had to go back to school today and get the cords.
So you're borrowing it?
I'm borrowing it. What I have is the school is, we filled out equipment, like equipment tags or cards, basically. So the school knows, okay, these items that belong to us are located here, right? So it's kind of like I got a checkout chart for both this computer and this document camera. I had bought a little document camera and it stinks. It's like not, you know, you have to spend still a decent amount of money to get a document camera this good. So, all right, got a bunch of stuff up on my screen and darn it, I'm gonna, you know, Tom had asked me about power probes. And he said, can you test your starter with the power probe? You can test a lot of stuff with the power probe. And this is, you know, you guys are probably laughing at mine because this is one of the old ones. I think this is version 2.0 of the power probe. So my original power probe that I destroyed didn't have a light. This one's got a light and it makes little noises. But I know the new power probes even have like a little multimeter built in there. Now, for those of you who have never seen a power probe is kind of like this particular one's like a logic probe. It's got a ground wire on it. So if I hook that up to there, it's saying, hey, you're going to ground because it connects to both the positive and negative battery terminals. It's got these real long cables. And it basically allows you to activate components pretty easily. So I get my eyes going here. For instance, if I wanted to test the relay, okay, if I hook on the other side of the control circuit, it shows me that I have continuity because it's measuring that ground. And if I hit the button, I can click the relay and function it, okay? Now, built into the power probe, it's got a little circuit breaker in here, and I forget what it's rated at, but I want to say it's like 8 amps or so. So it's a way for you to see where you have power, see where you have ground, give something a ground, or give it power if you want to. And, you know, I always think like here in America, we're like superhero crazy, right? And one of my favorite superheroes is Spider-Man. And a famous line from Spider-Man is, "With great power comes great responsibility." I look at the power probe is it's a tool with great power, but it also requires great responsibility in that if I give something power that's not supposed to have power, I could burn something up. And I've done that from experience. I thought I was on the ground circuit of some old Ford EQ4 something. But I thought I was on the ground circuit of a computer, and I wanted to give something ground, and I gave it power, and ended up basically burning a computer driver up in this old Ford. So like you can definitely destroy stuff with this if you're not careful. So it is super nice and convenient. We don't have, well, actually I should take that back. We have a few of these at ARC. We don't check them out of the tool room because we learned within the first week of us trying to do that, we had students burning up all kinds of stuff right and left on their own cars and school cars. And we were like, okay, time out. That's not going to work. So now Tom's question is, could I do some tests with the power probe on a starter circuit? Well, I could. So here I have that Volkswagen starter we looked at last week. I could, hook this guy up to ground. I'm going to just connect to the starter case here. You can see that when I hook up my power probe, it sees that it's ground. You can hear it doing its thing. I'll do it where it's actually on the screen. So on the case, it's ground. To the solenoid, it's ground. But I can kind of function the solenoid, but I can't flow enough amps through the power probe to actually get the solenoid to engage. Because remember, it's only got like an 8 amp circuit breaker. It's going to take 20 amps or more to actually engage the starter drive. So I could do some tests. If I had a relay that controlled the starter, I could function the relay with the power probe and maybe get that to move the starter. But it would be hard to function the starter itself with nothing but a power probe. They are super useful, but they are super easy to burn stuff up. Okay. All right. Last tech tip. This is really what I wanted to get to tonight. I've done this demo before where we were doing some resistance testing. All right. We took our meters, we set them to measure ohms. And I said, hey, always start off by, testing out your leads and stuff. I'm trying to get my leads untangled. It's amazing how tangled up stuff will get on your workbench. So I'm going to measure the resistance of my leads. And remember I said, hey, the problem with your meter when he's set to measure ohms is that if I measure the resistance of this little tiny wire right here, I got 0.13 ohms there. Well, now I'm going to take this nice cable that I made for an electric go-kart we were working on, and he'll measure about the same amount of resistance. And so remember, when your meter is set to ohms, he's putting out such little amounts of current that he can't tell the difference between this cable and this little wire right here, right? And so that's why I've said over and over, like I always recommend you do dynamic testing whenever possible. So here's an example. Here I have a spark plug wire. And if you look in like an old school repair manual, they'll talk about, hey, if you want to test a spark plug wire, put your meter on ohms. And touch the terminal, see how many ohms you have. You should have no more than 1,000 ohms per inch. Well, I have 4,135 ohms is what this is saying, or 4.135K, right? So that's less than the spec. So that means that this wire is okay. It's supposed to have some resistance to reduce radio frequency interference, and that's why they call it, I don't know if you guys can read that label, but it says it's a a suppression cable. It's supposed to suppress electrical noise. So it doesn't actually use a solid core piece of wire. It actually uses a piece of fiberglass in there for the cable. But that tests out okay. That being said, the meter doesn't put very much current flowing through this actual cable. A better way to test a battery cable, a more dynamic way, would be to, although I could use my meter, you know, I feel like that's kind of a bench test. And so it gives me some information, but a better way would be to put one of these spark intensity testers and run the car and see, okay, if I had this spark intensity tester on there, is this thing actually able to jump a 20,000 volt gap and make a nice bright blue spark in that? And that would tell me that the integrity of my cable is good. Not only do I have continuity through here, but it can transfer that high voltage, high intensity spark all the way to the end of the cable and get it to jump this gap. So that would be a better test because it's more dynamic, right? So although, you know, ohms testing has its purpose, it's not very dynamic. It's more of what I call bench testing, and you can miss things. So like in the case of this battery cable, let's say the I don't know, let's say the insulation right here was maybe a little bit where I drew on it there. Let's say the insulation there was a little bit worn, and that was causing it to short to ground on the engine a little bit when it just touched it. Well, I could ohms test it and never see that. But if I put it on the car, put a big gap on there and tried to run it, it would likely the cable would start breaking down and start arcing where the insulation is broke down. So anyways, dynamic test wherever possible. Okay, one last, go ahead.
Are you doing lab?
Am I doing lab? This is kind of like my lab, if you will, for our class. One last tech tip for you. Don't let your meter leads get on a hot exhaust manifold or get caught into stuff. And when your meter leads, if they're good leads, they're not like, once you move beyond like the cheapy Harbor Freight meter, these things have kind of an oddball lead size anyways. Once you're on a real meter with normal leads, the leads are made so that the outer covering is either going to be red or it's going to be black, right? But the layer of insulation underneath that is going to be white. So you can see that this one got a little melted and you can see the white underneath there, right? So that's done that way on purpose to help you identify if you have a cut or a problem in one of your leads. So a quick way to check is just look for any white nicks or spots on your leads, because the insulation underneath the outer layer is going to be white. This one, of course, here is melted. The lead still works okay, and the insulation's not melted all the way through. However, if I zoom in on this lead and I focus this camera again, it says that this is a Cat 3 lead that can handle 1,000 volts. Well, guess what? This lead is no longer a Cat 3 lead that could handle 1,000 volts and 10 amps and stuff, because its integrity is compromised right here. So check your leads very carefully. When we think about the CAT rating or category rating of our meter, and this becomes super important if you're working on electric vehicles or hybrids, where you're going to be measuring possibly some stuff that might be high voltage. It's not just the meter, but are the leads also Cat 3 rated? And then are those leads in good shape? Because if they're not, that could be a dangerous situation that could hurt you, possibly even cost you your life. So dynamic test where possible, and then always test your test equipment and inspect. Okay, so those are my tips for you for this week. And you got to see the power probe in action a little bit. Great tool. You got to be really careful with those things. So it's really easy to burn stuff up.
I got a question.
With the power probe. Okay, yeah, go ahead.
I don't know if it's you or me, but is there a way you can turn up the volume, how you're talking?
It's probably, well, it probably could be me in that my microphone is in the camera. So when I move over to the document camera, I'm a little further away from it.
Okay.
But guess what? We're done for tonight. So I want to let you guys get on to your normal lives, unless anybody has any more questions. If nobody has any other questions, I'll go ahead and let you get back to your normal lives. Do not forget, speaking of questions though, if you go to the discussions tab, there is a tech help thing. So if you're working on a car, you got something weird going on, your meter's doing something weird, you could always post something here on tech help and I can get to you and help you on that as well. So, all right. Have a great rest of your week. Have a good weekend. Don't forget on Saturday, you'll have 2 things that are due if you haven't already done those. I know some people have done them already, but that is that there is a little quiz that we saw tonight that's coming up due, and the discussion on the elimination of gas-powered cars for California in 2035. So definitely some big stuff to think about. All right.
Can you do a one-on-one?
What's that?
Can you do a one-on-one chat?
Afterwards, right now? Sure.
Yeah.
I'll go ahead and stop the recording. You guys have a great night, and we'll catch you next time. And you're welcome to stay, or you're welcome to go, but I'll go ahead and shut this recording off now. All right.
Thank you. Good night.
Good night, guys.